Hi, this is Dan Groninger for GE Inspection Technologies, and welcome back to our instructional series on the Mentor EM, or eddy current instrument. Today we're going to take a look at an example of an app for the EM. It's a guided workflow, so it steps through a number of calibration steps for doing a basic weld inspection. So for this app, we need one of our cross-wound weld probes. It's a differential probe with coils wound at 90 degrees to each other. So it's fairly insensitive to liftoff effects, but does a great job of detection of cracks and flaws in material for doing surface inspection. So we're going to use the Weld Dual Frequency app. It's one in the lower right here. Give a long hold on the app to launch it. And the first panel of the app, we have some basic welcome information. What is the application we're trying to solve here? Well, we're going to look at a piece of welded material. I have a sample here. It's basic steel, has a paint layer on it. There's a weld running down the middle, and I have a couple of known defects, EDM notches in the weld and in the plate itself. Now, this is the welcome panel to the app. You notice I have a go-to button down here in the right-hand corner called View PDF Procedure. If I click that, it will take me to a different panel in the app. And here I have a PDF document that describes the procedure used for the weld inspection. There's drawings of the weld sample. If I wanted to look more closely at that, I can zoom in. I can pan this around using my finger so I can get into a good bit of detail there. Another go-to button takes me back to the first panel. I can also get there through a couple of buttons on the navigation bar at the very bottom of the screen. I have one that shows a table of contents. That's a listing of all of the panels in this app. And I can move back and forth. I can randomly go to any panel if I choose. You can close that. Then I have forward and back buttons, right arrow, left arrow. So if I click the right arrow, that's forward, and that will take me to the next panel in this app. Or I can just choose to click the equipment button. I went to the table of contents, went to next. On this panel of the app, we have a list of equipment required to carry out the test. We have a picture here on the upper right of our standard weld kit. That includes the cable, the probes, actually two different sizes of the weld probe plus an absolute probe and a cable suitable for doing coating measurements. Basic weld standard with milled notches at 0.5 millimeter, 1 millimeter deep, and 2 millimeters deep. Some 20 thousandths plastic shims attached to it for calibrating liftoff. Comes with a roll of tape, some other things. So if we go to the next panel of the app, now here's where things get interesting. We begin to combine instruction on the left with some actual instrument operation on the right side of the screen. So you see I have one Lysis view, an impedance plane, sometimes called a spot view. You notice the crosshairs, the origin of this has been offset towards the bottom of the window. All of that's controllable. You see a little dot, red dot at the very bottom left corner, and that's our signal. And the red dot at the very edge of the Lysis indicates that the signal is actually off screen at the moment. So one of the first things we do with any eddy current instrument is we go to our standard, we put the probe down on a clean piece of metal on the standard, and we hit the balance button. And you notice my dot has now moved right to my origin. The balance button is the button on the nav bar that looks like a crosshair in a rifle scope. Beside that is the freeze button, snowflake for the freeze button, and a clear button to clear recorded signal. Now you notice my dot is nicely centered at the origin. If I pick the probe up, there's my liftoff curve for that probe on steel. And we play a little trick. We'll get into more detail on how the front end of the Mentor instrument works, the Wheatstone bridge, and the cycle table. We'll talk more about those in a more advanced discussion. But one of the tricks that we can do in the Mentor is configure the Wheatstone bridge at the front of the instrument in different ways on different time cycles in multiplexed operation. And we're actually taking advantage of that in this app. We keep most of that in the background where you don't have to think about it too much. But on this panel, and anytime you see the red trace, we've set the instrument up to treat this probe like an absolute probe. So even though it's a differential probe, there's two coils in there. On the shot that we're viewing on the screen, we are only driving one of the coils as an absolute probe. It's a little trick that we can play in the Mentor that's not very readily done on other instruments. But what we're going to do here is set this up, and we're going to calibrate the gain and the phase angle to give us full screen deflection. And you notice I used some gestures there. So I can reduce the gain by putting two fingers on the screen and moving them closer together. So pinch together reduces gain. Move the fingers apart as you would maybe on your cell phone to make a picture bigger. That will increase the gain. And I can tap up and down and hit freeze. That'll keep it on the screen, so now I can let go. Take my probe off. I can adjust it by using the pinch gesture. I can rotate that signal by putting my two fingers on the screen and twisting. Okay. I can also do these things by opening a menu, and I can control the gain in smaller steps and with more precision by opening a menu and moving things around that way. Okay. So I get my signal to full screen height that way. I go to my next panel, and here you see I have some pictures to go with my instructions. It says put the probe on the area to be inspected, and that means come over here. So we go to bare metal, balance at 0. I come over to my weld sample, and when I put my probe down, you'll notice my dot is no longer at the center. It's about 1.5 divisions up. What's up with that? Well, the material has some paint on it. So now what we're going to do is compare where the dot is on the painted material to where the dot would be on bare metal. And then I take one of my 20,000 shims and I put that on the bare metal. Well, now my deflection is already greater than what it was on the painted metal. So that plastic shim isn't very good for our purpose. I happen to have a sheet of paper here. So there again, there's bare metal in the standard. There's one sheet of paper. So one sheet of paper, paint. So the paint's a little bit thicker than one sheet of paper. So I fold my paper over. There's two sheets of paper, two thicknesses of paper, paint. Two thicknesses of paper. It's very close. So we can say the paint, we can measure the thickness of those folded over sheets of paper. If I were doing this for real, I would have a bigger collection of plastic shims in various thicknesses, and we could very accurately determine the paint thickness. We'll go to our next panel, and this is where now we're looking at a different time slice in multiplexed operation. So I put my probe on the standard, and I slide across the 1 millimeter notch, and I get a response that is about 100% screen height. So it goes from the origin in the middle to the edge of the display, and the notch is vertically up. If I turn my probe 90 degrees and slide it across the same notch, my response goes the other direction, 180 degrees out. And that's just a feature of our cross-wound weld probe. A transversely oriented flaw to the probe will give one indication. A longitudinal flaw will be 180 degrees out. Okay. Next, we have a panel with some instruction, some pictures of how to move the probe over the weld to do the inspection. We also have a video. The video won't come across really well on the remote screen view. In fact, it doesn't come across at all, so we'll skip that. But suffice it to say that if you were sitting in front of the instrument looking at the screen, you would have seen a live action video of a person moving the probe across the flaw. I apologize for that coming across as well on this video because of the mechanism I'm using to record. And then we have our inspection panel. So what we're going to do is we've already calibrated on our standard with 2 sheets of paper. We'll do a balance. So now the paint thickness, I still have my red, my liftoff channel, showing me contact with the metal, but through the paint thickness layer. And I have the green trace on the right, which we're going to use for flaw detection. So if I go back and forth over the probe, there we begin to get an indication from a notch in the weld. Okay. If I go down the length of the probe, there's a notch in the other orientation. So I might want to give a little bit more gain to my inspection to get a better view of that notch. Notch one way, forth, and there's the notch that way. There's also a notch right along the edge of the weld right there. Okay. So basic surface inspection. And with that, we'll wrap the video, or we'll wrap this episode of our instructional videos. Having looked at a basic weld inspection, basic surface inspection, a little more complex than some in that we made use of a 2 time cycle multiplexed operation where we ran the probe on one cycle as an absolute probe for measuring coating thickness. On the other cycle, we ran it as a differential probe to give us good sensitivity for detecting notches in the material. And thank you for joining me, and we'll come back the next time and look a little bit more at surface operation and some of the gestures that you can use with a strip chart to help with analysis. So thank you for watching. Again, this is Dan Groninger for GE Inspection Technologies, and see you next time.